The smell of diesel fuel hung thick over the shipyards as workers finished welding the final plates on hull U-53. Radio broadcasts from Berlin spoke confidently of decisive naval campaigns to come, while dockworkers moved ammunition and torpedoes into cramped storage compartments below deck. A lieutenant commander stood on the pier, reading aloud from a technical specification sheet: 760 tons surface displacement, twin MIN M6 V4046 diesel engines producing 2,400 horsepower combined, 553.3 centimeter torpedo tubes. The numbers promised offensive power. What the specifications did not mention was the 1.3 cubic meters of living space per man, or the 90 to 95% relative humidity that would fill the hull within days of departure. Commanders expected Wolfpack tactics to strangle Britain's supply lines. The reports would soon reveal a different enemy: the air inside the submarine itself. On the trial slate at the naval yards sits a Type 7 hull, designated for immediate Atlantic service. The specifications are precise and unforgiving. Approximately 760-ton surfaced, twin MIN M6 V40/46 diesels producing roughly 2,400 horsepower combined when running at full load, 553.3 centimeter torpedo tubes arranged with 4 forward and 1 aft, and crew accommodations that can only be described as Spartan. The design philosophy privileges weapons capacity and operational reach over habitability. There is no refrigeration system for food storage. There is no air conditioning for crew comfort. There is only basic ventilation, limited by the need to preserve battery power and avoid detection when submerged. In staff memoranda circulating through the Kriegsmarine High Command, Admiral Karl Donitz anticipates decisive results from Rudeltaktik, Wolfpack operations, once several hundred boats can be fielded simultaneously across the convoy routes. The near-term constraint is identified as production capacity and trained crew availability, not crew comfort or long-term habitability. Engineering trade studies explicitly accept reduced living standards in exchange for additional torpedo storage, extended fuel capacity, and more powerful diesel engines. One internal planning document states the calculation plainly: every ton devoted to crew comfort is 1 ton not available for offensive capability. By 1940, roughly 50 boats are conducting patrols from German ports, operating from bases at Kiel, Wilhelmshaven, and other North Sea facilities. But the decisive logistical shift comes with the fall of France later that year. The capture of French Atlantic ports, Lorient, Saint-Nazaire, Brest, La Pallice, and Bordeaux, extends patrol arcs by 700 to 1,000 nautical miles and increases dwell time off the British sea lanes by days or even weeks. The concrete submarine pens built at these locations provide protected berthing and rapid turnaround, cutting the transit time through dangerous North Sea approaches. The contrast between offensive capability and crew endurance becomes clear in early operational reports. The Type 7 hull meets or exceeds combat specifications for weapons load, speed, and range. However, no naval standard exists for sustained air quality below the surface. Oxygen depletion, carbon dioxide accumulation, diesel exhaust residue, and battery compartment off-gassing are treated as unavoidable operational facts rather than engineering problems requiring systematic solutions. The trade-offs are intentional and documented: firepower first, habitability second. Even as boat numbers rise through 1940 and 1941, Britain is already expanding escort production and deploying new detection technologies faster than Germany can mitigate the growing crew endurance limits. Allied shipyards are launching corvettes, frigates, and destroyer escorts at rates that will soon outnumber available U-boats. Radar development on both sides of the Atlantic advances rapidly, and the advantage begins to shift. The Wolfpacks will have their moment of success, but the underlying mathematics of industrial production and human endurance are already moving against the U-boat arm. From the newly completed Atlantic pens at Lorient, Type 7 crews depart on patrols averaging 49 days at sea. The boats are loaded beyond their designed stowage capacity, with food supplies crammed into passageways, bunks, and any available void space. Fresh provisions are exhausted within the first week. After 2 weeks at sea, mold growth becomes a common and accepted condition as relative humidity inboard remains between 90 and 95%, with no effective means of dehumidification. Bread turns green within days. Clothing never fully dries. The interior surfaces of the hull weep with condensation. Ventilation cycles are strictly rationed to conserve fuel and reduce the risk of radar or visual detection when surfaced. When the boat surfaces at night to charge batteries, the crew inhales a mixture of diesel combustion products, carbon monoxide, nitrogen oxides, and unburned hydrocarbons that infiltrate through hatches and ventilation trunks. Submerged operations present a different set of hazards. Battery compartments emit hydrogen gas during charging and can release chlorine gas if contaminated by seawater intrusion. Medical officers attached to submarine flotillas record the predictable symptoms of carbon dioxide accumulation and oxygen depletion during extended silent running. Headaches, dizziness, nausea, slowed cognitive function, impaired decision-making, and physical exhaustion. Comparable submarine medicine literature from multiple navies documents similar hazards from carbon monoxide, nitrogen dioxide, and chlorine exposure under confined conditions. The human body can tolerate short-term exposure to degraded air chemistry, but the cumulative effects over weeks at sea are severe. Sleep is disrupted by watch rotations, mechanical noise, and the constant low-level stress of operating in hostile waters. Nutrition deteriorates as fresh food spoils and the diet shifts to canned goods and preserved rations that lack essential vitamins. Weight loss of 5 to 10 kilograms per patrol is routine and expected. The physical environment inside a submerged Type 7 is mechanically hostile. Temperatures fluctuate between near freezing in northern waters and oppressive heat in tropical zones. With no climate control beyond opening or closing ventilation valves, the hull conducts temperature directly from the surrounding seawater, creating cold spots where condensation accumulates and hot spots near the diesel engines and electric motors. Crew members sleep in shifts, often in damp clothing, on bunks that reek of mildew and unwashed bodies. Personal hygiene is limited to occasional sponge baths using minimal fresh water. Toilet facilities are primitive and frequently malfunction under pressure cycling. The psychological toll compounds the physical strain. Men live in close quarters with no privacy, constant noise, and the knowledge that depth charges or torpedoes could end their lives in seconds. The monotony of patrol life, long periods of waiting punctuated by brief moments of intense action, creates a unique form of stress. Crew cohesion and discipline are maintained through rigid naval hierarchy and shared suffering, but morale problems surface during extended patrols, particularly when operational success is low and losses among other boats are known. By year's end, the campaign presents a grim paradox. Tonnage sunk by U-boats continues to rise, reaching peak monthly totals that alarm Allied planners. Yet of 179 boats that departed on patrol during 1941, 62 do not return. This 35% loss rate foreshadows a brutal attrition curve that will only steepen as Allied countermeasures improve. The human cost inside the surviving boats remains largely invisible in official German war reports, but the cumulative physiological and psychological damage is real and measurable. Staff planners at the Seekriegsleitung, the Naval Warfare Command, work through operational balance sheets that weigh fuel consumption, torpedo expenditure, and battery endurance against patrol aggressiveness and target opportunity. The informal instruction passed down the chain of command remains consistent. Press attacks until the last torpedo is expended, then return to base for refit and rearmament. Aggressiveness is rewarded. Caution is questioned. The doctrine prioritizes offensive action above all other considerations, including crew welfare. Internal engineering proposals circulate for improved forced ventilation systems and chemical air scrubbing apparatus to reduce carbon dioxide levels during prolonged submergence. These proposals carry weight penalties that compete directly with electronics upgrades, additional torpedo storage, and enhanced sonar equipment. The institutional priority remains clear: weapons and sensors first, habitability improvements last. Each design review concludes with the same calculation: tonnage sunk per patrol must increase, and crew comfort is an acceptable sacrifice to achieve that goal. Meanwhile, intelligence reports from the United States indicate that American fleet submarines are beginning widespread deployment of soda-lime carbon dioxide scrubbing systems. These chemical absorbers allow extended submerged operations without debilitating air quality degradation. United States Navy fleet boats also feature significantly greater internal volume per crew member, approximately 2.8 cubic meters compared to the Type 7's 1.3 cubic meters. This difference translates directly into better air circulation, more storage for provisions, improved crew quarters, and enhanced overall habitability. The human factors gap between German and American submarine design becomes increasingly apparent to analysts who study captured equipment and interrogate prisoners. The strategic expectation driving German submarine doctrine, maximize tonnage sunk regardless of cost, begins to collide with physiological limits that manifest as longer turnaround times between patrols, more frequent equipment failures caused by moisture and corrosion, and declining crew performance during the final weeks of extended operations. Patrol commanders report increased difficulty maintaining watchkeeping standards after day 30. Mechanical breakdowns attributed to poor maintenance accumulate. The connection between degraded air quality, crew fatigue, and operational effectiveness is documented in after-action reports but does not translate into design changes or doctrinal modifications. A planning memorandum from a staff medical officer captures the emerging risk in stark terms. The physics of confined air chemistry may ultimately defeat aggressive operational doctrine as Allied detection capabilities improve and available surface time shrinks. The note is filed and apparently not acted upon. Operational necessity drives immediate decisions. Long-term sustainability questions are deferred. The institutional culture of the Kriegsmarine prioritizes offensive spirit and technical innovation in weapon systems, while treating crew endurance as a secondary factor that can be managed through selection and training rather than engineering solutions. The winter of 1941 marks the high point of U-boat effectiveness in the Atlantic. Merchant ship losses mount faster than replacement construction can offset. British food stocks dwindle. Fuel rationing tightens. Yet even during this period of tactical success, the underlying trends are working against the submarine campaign. Allied escort numbers are growing. Radar technology is improving. The air cover is expanding. And the human limits inside the Type 7 hull are becoming increasingly difficult to ignore. The U-boat training facility at Kiel runs a continuous pipeline of recruits through progressively demanding courses designed to prepare crews for Atlantic operations. One critical phase involves sealed compartment drills that simulate prolonged silent running under depth charge attack. Recruits are sealed inside training chambers with reduced ventilation flow, elevated carbon dioxide levels, and intensive task saturation focused on damage control procedures. The training staff monitors oxygen and carbon dioxide levels, deliberately pushing conditions to the edge of tolerability to build crew resilience and test individual limits. British Admiralty interrogation reports compiled from captured U-boat survivors describe the training regimen as exhaustive in procedural detail but resource-constrained in terms of comfort equipment and spare parts availability. Recruits learn to operate every system on the boat, perform emergency repairs under simulated combat conditions, and maintain discipline during simulated crisis scenarios. The emphasis is on technical proficiency and mental toughness. What the training cannot fully replicate is the cumulative physiological effect of weeks at sea, the progressive exhaustion from poor sleep, inadequate nutrition, constant dampness, and the grinding psychological stress of operating in a hostile environment where any moment might bring sudden death. The training pipeline expands dramatically through 1942 and 1943 as the Kriegsmarine attempts to maintain crew strength in the face of mounting losses. Thousands of men cycle through abbreviated courses, with training time compressed to meet the urgent demand for replacements. Classes that once took 6 months are shortened to 4 months or less. Simulator time is reduced. Sea trials are abbreviated. The expectation is that procedural perfection and ideological commitment will compensate for reduced training time and offset the physiological strain of extended combat patrols. Reality delivers a different outcome. Training can teach men how to operate valves, repair machinery, load torpedoes, and follow emergency checklists. Training cannot prepare the human body for the cumulative effects of weeks spent breathing air with elevated carbon dioxide, reduced oxygen, diesel fumes, battery gases, and the pervasive humidity that breeds mold and disease. Men arrive at operational flotillas with excellent technical skills but no real preparation for the physical and mental grinding down that defines life aboard a combat patrol. The veterans who survive multiple patrols develop adaptive strategies, sleeping whenever possible, eating sparingly to reduce digestive distress, focusing narrowly on immediate tasks to manage anxiety, But these coping mechanisms cannot be taught in a classroom. By mid-1942, the submarine school at Kiel was producing competent watchstanders, mechanics, and weapons operators at the rate of several hundred per month. Yet nearly half of the trained personnel will never complete a successful combat patrol. Some die on their first mission. Others are killed during training accidents or in transit to forward bases. Still others are reassigned when boats are sunk before they can join their crews. The arithmetic of attrition outpaces even the accelerated training throughput, creating a personnel deficit that will only worsen as the war progresses. Battery charging begins shortly after dusk, when the submarine surfaces under the relative cover of darkness. Hatches are cracked open to vent accumulated heat and exhaust fumes, while the diesel engines roar at full load, driving generators to restore the battery banks to full charge. The procedure is choreographed down to the minute, with crew members rotating through duties to minimize individual exposure to diesel combustion products while maintaining operational readiness for emergency dive. U-96 is well documented in wartime records and post-war histories, providing detailed insight into the daily operational rhythm of Atlantic patrol boats. The crew follows a strict routine, exhaust management procedures to prevent carbon monoxide accumulation, watch rotations timed to balance rest and duty, and continuous monitoring of battery compartment chemistry to detect early signs of chlorine or hydrogen gas release. German boats in the early war period lacked redundant air purification equipment, making proper exhaust management and ventilation discipline critical to crew survival. The expectation that brief surface periods at night will provide sufficient fresh air and battery charging time collides with the rapidly improving Allied air search radar and increased patrol aircraft density. British and Canadian maritime patrol bombers equipped with ASV Mark II and Mark III radar can detect surface submarines at ranges exceeding 10 miles, even at night. This forces U-boats to compress charging windows into shorter, riskier evolutions, often diving before the batteries reach full charge. Inside the pressure hull, the consequences are immediate. Reduced battery capacity limits submerged speed and endurance, while abbreviated ventilation time leaves the atmosphere heavy with residual diesel fumes, moisture, and accumulated carbon dioxide. Medical documentation from submarine operations across multiple navies identifies diesel combustion products, carbon monoxide, nitrogen dioxide, sulfur compounds, as recognized respiratory and neurological hazards in confined spaces. Carbon monoxide binds to hemoglobin more readily than oxygen, reducing the blood's oxygen-carrying capacity and causing headaches, confusion, and nausea at relatively low concentrations. Nitrogen dioxide irritates mucous membranes and can cause delayed pulmonary edema. The sulfur compounds in diesel exhaust contribute to the characteristic acrid smell and can trigger respiratory distress in susceptible individuals. The crews adapt as best they can. Men learn to recognize the early symptoms of carbon monoxide poisoning: dull headache, fatigue, difficulty concentrating, and rotate to less contaminated areas of the boat when possible. Diesel mechanics become expert at tuning engines to minimize incomplete combustion and reduce exhaust opacity. Watch officers time surface periods to maximize fresh air intake while minimizing radar exposure. Yet every adaptation has a cost. Reducing surface time improves survivability against air attack but worsens air quality below. Diving deeper avoids escort ships but increases psychological stress and reduces battery endurance. The tactical equation offers no good choices, only trade-offs between competing risks. An engineering calculation illustrates the fundamental problem. Removing 1 ton of crew habitability equipment, bunks, ventilation ducting, carbon dioxide absorbers, freshwater storage, creates space and weight margin for 1 additional torpedo. On paper, this trade makes sense. Each torpedo represents potential tonnage sunk, contributing directly to the strategic objective of interdicting Allied supply lines. In practice, the calculation erodes crew performance margins at sea, reducing the overall effectiveness of each patrol and increasing the likelihood of errors, equipment failures, and diminished combat capability during critical engagements. Maintenance logs compiled by Atlantic Flotilla staff reveal a concerning trend through the summer and fall of 1942. A rising proportion of mission-impacting equipment failures directly attributed to moisture intrusion and corrosion damage. Electrical relay failures, insulation breakdowns, and misfires in damp motor armatures occur with increasing frequency, sometimes forcing boats to abort patrols and return to base for repairs. The interior environment of a Type 7 submarine is mechanically hostile in the extreme. Relative humidity remains at or above 95% continuously during submerged operations. Salt aerosols circulate through ventilation systems. Condensation accumulates on cold metal surfaces and drips onto electrical equipment. Drying time between patrols is limited by operational tempo and the urgent need to rotate boats back to sea. The expectation underlying the maintenance schedule is that planned refit cycles conducted at established intervals will maintain equipment reliability within acceptable parameters. Reality demonstrates otherwise. Compressed yard periods driven by mounting U-boat losses and the need to maximize available hulls at sea leave dehumidification upgrades and improved ventilation systems at the bottom of the priority list. Weapon systems receive immediate attention. Hull integrity issues are addressed. Electronics are repaired or replaced as parts allow. Crew habitability and air quality improvements are consistently deferred in favor of more urgent operational needs. The cause and effect relationship between humidity and equipment reliability is direct and well understood by the maintenance personnel who work on the boats. Every percentage point of relative humidity not removed from the interior atmosphere shortens the service life of electrical components and increases the probability of in-patrol failures. Insulation designed for dry conditions breaks down rapidly when continuously soaked. Relay contacts corrode and stick. Motor brushes wear unevenly when operating in moisture-saturated air. Battery terminals develop sulfate deposits.
Torpedo tubes jam. Periscope optics fog.
Radio equipment becomes unreliable. Engineering solutions exist. Dehumidification equipment using desiccant beds or refrigeration cycles could significantly reduce interior moisture levels. Improved hull insulation could minimize condensation on cold surfaces. Sealed electrical enclosures could protect sensitive components from salt aerosol exposure. Yet implementing these solutions requires weight and volume that compete with weapons, fuel, and provisions. It also requires production capacity, skilled labor, and raw materials that are increasingly scarce as the war effort strains German industrial resources. The institutional decision is made repeatedly: accept higher equipment failure rates rather than sacrifice offensive capability. Flotilla commanders and boat captains learn to work around the problem. Patrol plans include contingency time for equipment troubleshooting. Crews become expert at field-expedient repairs using limited tools and spare parts. Electricians develop techniques for drying out soaked components using waste heat from the diesel engines. Yet these adaptations cannot overcome the fundamental reality that the boats are operating beyond their designed environmental limits, and the cumulative degradation accelerates with each patrol cycle. By late 1942, the invisible enemy inside the hull water in its vapor phase, permeating every void space and surface, is causing as much operational disruption as Allied depth charges and air attacks. The fleet's material readiness is declining not because of enemy action alone, but because the basic design of the Type 7 submarine did not adequately account for the harsh reality of prolonged combat operations in the North Atlantic environment. The engineering trade-offs that seemed reasonable in 1939, offensive punch over habitability, are now revealing their full cost in reduced availability, increased maintenance burden, and declining overall effectiveness. Long silent runs at reduced oxygen and elevated carbon dioxide concentrations degrade watchkeeping performance and slow decision-making processes. The human brain is exquisitely sensitive to changes in blood chemistry. Even modest increases in carbon dioxide levels, from the normal atmospheric concentration of 0.04% to 2 or 3%, cause measurable impairment in cognitive function, alertness, and reaction time. Prolonged exposure to reduced oxygen levels compounds the effect, creating a state of chronic hypoxia that manifests as persistent fatigue, difficulty concentrating, and slowed information processing. Depth charge attacks extend crew stress exposure well beyond normal combat duration. A typical depth charge barrage may last hours, with escorts circling overhead and dropping explosives in patterns designed to bracket the submarine's estimated position. The boat runs silent and deep, with all unnecessary equipment shut down to minimize noise and conserve battery power. Men lie motionless in their bunks or stand frozen at their stations, listening to the mechanical pinging of active sonar and the distinctive splash and rumble of depth charges exploding in the water column. Near misses produce violent shock waves that flex the pressure hull, shake loose equipment, crack pipe fittings, and shatter gauges. The cumulative psychological impact of repeated exposure to this level of sustained threat is profound. Survivor interrogations conducted by British and American intelligence officers and post-war naval medicine studies document the predictable psychological effects of prolonged submarine combat operations. Sleep fragmentation becomes chronic, with watch rotations and emergency alerts disrupting normal circadian rhythms. Anxiety levels rise, particularly during depth charge attacks and when oxygen levels drop below normal thresholds. Interpersonal conflicts increase under the stress of close confinement and shared danger. Some men develop acute stress reactions, panic, paralysis, uncontrollable trembling, that render them temporarily unfit for duty. Others display remarkable resilience, maintaining professional performance under conditions that would break most individuals. Propaganda materials produced for German domestic consumption during the war years emphasize iron discipline, Nordic toughness, and unwavering commitment to duty. The documentation from crew interrogations and post-war medical analysis shows a more complex picture. Yes, discipline is generally maintained. Yes, most crews continue to function under extraordinary stress. But the cumulative fatigue becomes undeniable after approximately 18 to 20 days of heavy submerged operations. Performance declines. Errors multiply. Judgment suffers. The human body and mind can endure remarkable hardship for limited periods, but the physiological and psychological reserves eventually deplete. The contrast between doctrinal expectations and human capabilities sharpens as the war progresses. Doctrine presumes constant aggressiveness. Seek targets, press attacks, maintain combat readiness throughout the patrol. Physiology delivers diminishing returns, cognitive function declines, physical performance degrades, and the capacity to sustain high-intensity operations erodes with each additional day at sea. The institutional response to this growing gap is to emphasize willpower, selection, and training. The underlying assumption is that proper mental attitude and sufficient preparation can overcome physical limits. This assumption proves increasingly untenable as patrol durations extend and Allied pressure intensifies. Of 20 boats dispatched during one winter month in early 1943, over half failed to return to base. This 60% loss rate provides a grim snapshot of the accelerating attrition that will characterize the remainder of the U-boat war. The human toll inside the surviving boats, the accumulated psychological trauma, physical exhaustion, and degraded health, remains largely invisible to outside observers but is documented in medical records, interrogation reports, and post-war memoirs. The price of maintaining offensive operations under these conditions is measured not just in sunken hulls but in broken men. Allied technical intelligence analysts complete a detailed comparative assessment between a captured German Type 7 U-boat and a United States Navy Gatto-class fleet submarine. The physical comparison reveals stark differences in design philosophy. Internal volume per crew member measures approximately 1.3 cubic meters in the Type 7 versus roughly 2.8 cubic meters in the Gatto class, more than double the space allocation. Standard patrol duration averages 49 days for German boats operating from French Atlantic bases, compared to approximately 35 days for United States submarines operating in the Pacific theater. The American boats feature superior cold storage for provisions, more effective air handling systems, and better overall environmental control. The strategic finding embedded in the technical analysis is clear and concerning for the German submarine service. German crews are routinely operating beyond reasonable human factor design limits. The cumulative cost of this operational overreach manifests in multiple measurable ways. Average weight loss during a Type 7 patrol ranges from 5 to 10 kilograms per man, a level of nutritional deficit that indicates chronic caloric insufficiency and physical stress. Maintenance quality drifts as fatigued crews make more errors during refit periods. Recovery time between patrols lengthens as men require additional rest to regain baseline health and readiness. The comparison extends beyond simple volume calculations to examine specific systems and their impact on crew welfare. American fleet submarines carry ice machines for food preservation, allowing fresh vegetables and meat to remain edible throughout extended patrols. German boats carry no refrigeration and rely entirely on canned goods and preserved rations after the first week at sea, with predictable impacts on nutrition and morale. United States boats feature air conditioning systems that provide climate control and dehumidification, maintaining interior humidity below 60% even in tropical conditions. German boats have no such capability, with humidity remaining above 90% throughout most patrols. Battery ventilation illustrates another critical difference. American boats employ forced air circulation with external blowers that actively exhaust hydrogen and other battery gases to the outside atmosphere. German boats use passive ventilation that depends on natural convection and brief surface periods, resulting in higher concentrations of hazardous gases in crew spaces. Carbon dioxide scrubbing capacity is substantially greater in American boats, allowing extended submerged operations without debilitating air quality degradation. German boats have minimal chemical absorption capacity and must surface more frequently to ventilate, increasing vulnerability to air and surface attack. British interrogators who interview captured U-boat crew members note a recurring theme in the testimonies: grudging respect mixed with envy for Allied submarine conditions. German submariners are aware, through intelligence briefings, captured documents, and rumors, that their counterparts in American and British boats operate under significantly better conditions. What impresses Allied intelligence officers during these interrogations is the sheer endurance displayed by German crews despite the harsh conditions. Men describe accepting chronic discomfort, poor nutrition, and constant physical strain as simply the price of service. The professional competence and dedication remain high even as the material conditions deteriorate. Yet this very endurance carries a hidden cost that will contribute to the strategic defeat of the U-boat campaign. As Allied detection technologies advance and force Type 7 boats to spend progressively more time submerged, the human factor limitations become insurmountable obstacles. The physiological and psychological margins that allowed crews to function effectively during earlier, shorter submergence periods evaporate under the extended underwater operations required to evade radar-equipped aircraft and escort vessels. The design choices made in the late 1930s, prioritizing weapons and range over crew welfare, now constrain operational effectiveness more severely than any Allied countermeasure. The intelligence assessment concludes with an observation that proves prophetic: German submarine endurance, far from being a strategic asset, is destroying the U-boat arm from within. The very qualities that allow crews to tolerate extreme hardship, discipline, commitment, physical toughness, are being consumed faster than they can be replaced through training and selection. The human infrastructure supporting the submarine campaign is eroding at a rate that no doctrinal adjustment or tactical innovation can arrest. The war of attrition is being lost not only in terms of hulls and tonnage but in the progressive exhaustion of the men who crew the boats. With Allied ASV radar coverage and escort carrier deployments reaching comprehensive levels across the convoy routes, U-boats are now driven to remain submerged for more than 90% of operational hours during many patrol days. This fundamental shift in tactical reality transforms the submarine campaign from a surface ship with diving capability model to a true submersible force to operate primarily underwater. The physiological consequences are immediate and severe. Submerged endurance on battery power alone is theoretically approximately 48 hours before carbon dioxide accumulation reaches debilitating concentrations that force a surface or snorkel evolution to ventilate the hull. In practice, operational constraints often compress this timeline. High-speed, submerged maneuvering to evade escorts drains batteries faster. Depth charge attacks force prolonged silent running at minimal power output. Equipment failures reduce available battery capacity. The result is that boats frequently must surface or snorkel before carbon dioxide reaches critical levels, but often when tactical conditions make such exposure extremely dangerous. Chemical oxygen candles, solid compounds that release oxygen when ignited, are tried on selected boats as a potential solution to extend submerged endurance. These devices, similar to those used in emergency breathing equipment and aircraft oxygen systems, can supplement the boat's atmosphere with fresh oxygen without requiring surface ventilation. However, the candles introduce new hazards that limit their practical utility. They generate substantial heat during the oxygen release reaction, creating fire risk in the confined, fuel and oil-contaminated environment of a submarine interior. Several documented incidents involving thermal injuries and localized fires during candle use lead to restricted deployment and conservative usage guidelines. The service largely returns to reliance on manual air cycling and conservative submerged operational profiles rather than accepting the risks associated with chemical oxygen generation. The shocking realization crystallized in operational analysis by late 1943 is that the decisive limiter of U-boat effectiveness is not a new Allied weapon system, not superior enemy tactics, not even industrial production capacity. It is the fundamental chemistry of air in a sealed hull. This parameter was largely fixed by design choices made in 1939 and 1940, when the operational environment and mission profile were fundamentally different. The Type 7 was designed for surface operations with periodic brief dives to attack or evade. It is now being forced to operate as a true submarine, spending days at a time submerged, for which it is physiologically unsuited. Oxygen partial pressure in the atmosphere must remain above approximately 15% to support normal human cognitive function. Below this threshold, symptoms of hypoxia appear rapidly: confusion, poor judgment, slowed reactions, loss of consciousness. Carbon dioxide concentration must remain below approximately 3% to avoid acute symptoms of hypercapnia. Severe headaches, disorientation, respiratory distress. The Type 7 hull, when sealed and submerged, has a finite volume of atmosphere and no effective means of regeneration beyond ventilating to the outside world. The mathematics are unforgiving. 45 men consuming oxygen and producing carbon dioxide can render the atmosphere unbreathable in under 2 days, regardless of tactical considerations or enemy pressure. No amount of tactical brilliance can circumvent these basic physical constraints. Aggressive captains cannot will their boats to remain submerged longer than the air chemistry allows. Experienced crews cannot train their bodies to consume less oxygen or produce less carbon dioxide. Superior torpedo technology cannot compensate for the inability to approach targets because extended submergence causes crew incapacitation. The physics of confined air environments impose absolute limits that tactical doctrine must respect or face inevitable failure. The Type 9 boats, larger, longer-range variants designed for distant operations, fare somewhat better due to greater internal volume and proportionally lower crew density. But the Type 7s, which constitute the vast majority of the operational fleet, are trapped in an impossible situation. Allied pressure forces them underwater where they cannot survive for extended periods. Surfacing to ventilate exposes them to radar detection and air attack. The tactical solution space has collapsed to a narrow window of marginally viable options, none of which offer reasonable probability of mission success combined with crew survival. The Schnorchel, adapted from Dutch submarine technology captured during the 1940 campaign, permits diesel engine operation at periscope depth by drawing combustion air through a retractable mast while expelling exhaust below the surface. This innovation theoretically solves the fundamental dilemma facing the U-boat force. It allows battery charging and interior ventilation without fully surfacing, dramatically reducing radar cross-section and visual signature. The first operational installations began appearing on frontline boats in late 1943, with widespread deployment accelerating through 1944. Operational trials and field reports quickly document both the advantages and significant hazards associated with snorkel operations. The device functions as designed, permitting extended submerged patrols by enabling regular battery charging without surface exposure. However, several problems emerge that limit its effectiveness and introduce new risks to crew health and safety. Exhaust reingestion occurs when sea state or maneuvering causes the snorkel head to draw engine exhaust back into the air intake, filling the boat with diesel combustion products. Carbon monoxide poisoning incidents are documented in multiple boats, with one case aboard U-1228 requiring emergency return to base after crew members displayed severe symptoms of carbon monoxide toxicity. Pressure cycling creates another hazard. The snorkel head is equipped with an automatic float valve designed to seal the intake when waves wash over the opening, preventing seawater intrusion into the diesel engines. When this valve closes, the running diesels immediately create negative pressure inside the hull as they continue consuming air that can no longer be replaced from outside. The result is rapid pressure drop, sometimes exceeding 0.5 atmospheres, that causes severe ear pain, sinus barotrauma, and in extreme cases can rupture eardrums or cause pulmonary damage. Crew members learn to recognize the characteristic change in engine sound that signals valve closure and brace themselves for the pressure drop. But the repeated cycling causes cumulative physical trauma. Eye and airway irritation becomes a chronic problem during snorkel operations. The combination of diesel exhaust, elevated carbon dioxide from incomplete ventilation, and the damp, corrosive atmosphere causes persistent inflammation of mucous membranes. Crew members develop chronic coughs, red and swollen eyes, and difficulty breathing. The reduced flow rate through the snorkel compared to surface ventilation means that the air below never fully clears of contaminants. The boat operates in a state of continuous partial air pollution that is tolerable for hours but degrading over days. Acoustic awareness suffers dramatically during snorkel operations. The noise of running diesel engines and the sound of water rushing past the snorkel mast overwhelm the hydrophone systems used to detect approaching escorts. Boats running on snorkel are effectively deaf to acoustic threats, relying entirely on periscope observation for situational awareness. This sensory deprivation creates acute vulnerability to surface escorts that can approach undetected until they are at close range. Multiple boats were surprised and sunk by escorts that closed to attack range, while the U-boat crew remained unaware due to self-generated noise masking. Speed limitations constrain tactical flexibility. A snorkeling submarine can sustain only approximately 6 knots, barely faster than a surface merchant ship and far slower than pursuing escorts. This makes evasion difficult and approach to convoy targets extremely time-consuming. Patrol durations extend as boats spend days slowly maneuvering into attack position, increasing crew fatigue and reducing the number of attacks possible per patrol. The tactical advantage of radar invisibility is partially offset by the operational penalties of slow speed and degraded sensors. Official German naval narratives acknowledge that snorkel-equipped boats achieve improved survivability through reduced radar exposure. Loss rates decline compared to the catastrophic attrition of mid-1943. However, the internal documents and crew testimonies reveal that the snorkel imposes severe efficiency penalties that tactical doctrine cannot avoid. Patrols become longer, more exhausting, and less productive. Crew health deteriorates under the combined stress of extended operations, poor air quality, and the physical trauma of pressure cycling. The snorkel saves boats from immediate destruction but subjects crews to a prolonged grinding ordeal that drains effectiveness and morale. Allied air supremacy over the Bay of Biscay approaches has transformed the transit routes between French bases and the Atlantic operational areas into a gauntlet of continuous threat. Departure from port now equals immediate danger. Boats attempting to reach open ocean must run the narrows where British Coastal Command and United States Army Air Force's patrol aircraft maintain near-constant coverage using improved radar, searchlights, and air-to-surface weapons. The concrete submarine pens provide protection while in port, but boats must eventually sortie to conduct patrols, and the window of vulnerability during transit has become a killing zone. German naval directives circulating through the Atlantic flotillas explicitly acknowledge that crew exhaustion now exceeds material limitations as the primary constraint on operational effectiveness. The language is careful but clear. Men are breaking down faster than machines. Boats spend increasing time submerged on snorkel during transit, approach, and patrol, with correspondingly poorer air quality and longer exposure to the physiological and psychological stressors inherent in extended submergence. The cumulative burden shows in medical evaluations conducted during refit periods. Weight loss, vitamin deficiencies, respiratory problems, and psychological exhaustion are documented in crew medical files with increasing frequency. The fatality statistics tell the larger story with brutal clarity. Of approximately 40 to 41,000 men who served in the U-boat force during the war, roughly 28,000 are killed. A 68 to 70% fatality rate that exceeds the loss rate of virtually any other military branch in any combatant nation during World War II. Only approximately 156 boats surrendered at war's end in May 1945. The vast majority are sunk in combat, destroyed in port by bombing, or scuttled by their crews to prevent capture. The human cost is staggering and unsustainable. No training pipeline can replace losses at this rate. No selection process can find enough qualified men willing to accept near-certain death. The turning point, documented in both German and Allied records, occurs by mid-1944 when loss rates overtake any conceivable sustainable training and production capacity. The Kriegsmarine continues building boats. Type 21s with improved performance are under development and continues training crews, but the operational mathematics no longer support the campaign. New boats and fresh crews are being destroyed faster than they can be generated. The strategic calculus that justified the submarine campaign, interdict Allied supply lines, sink sufficient tonnage to strangle Britain, has failed. Allied merchant ship construction, particularly in American shipyards employing mass production techniques, exceeds sinking rates by wide margins. The convoy system, improved escort tactics, and overwhelming Allied air and surface superiority have neutralized the U-boat threat. What remains by late 1944 is a campaign of attrition that serves no strategic purpose beyond tying down Allied anti-submarine resources that might otherwise be employed elsewhere. The boats continue sailing. The attacks continue. Men continue dying in confined steel tubes at the bottom of the Atlantic. But the outcome is no longer in doubt. The human dimension, not merely tonnage calculations or technological factors, marks the decisive defeat of the Atlantic submarine offensive. The institutional willingness to sacrifice crew welfare for offensive capability, the design trade-offs that privileged weapons over habitability, and the doctrinal insistence on aggressive operations regardless of physiological costs have combined to destroy the U-boat arm from within. The campaign that once threatened Britain's survival has become a death ride for the men who crew the boats. They understand the odds. They know the statistics. Yet discipline holds, and boats continue to depart on patrols that offer little probability of success and high likelihood of death. The arm that once threatened to sever Britain's lifeline across the Atlantic now fights an enemy as implacable as any Allied weapon. The atmosphere inside its own hulls, the cumulative exhaustion of its crews, and the grinding attrition that cannot be overcome by courage, skill, or determination alone. In the immediate aftermath of German surrender, Allied technical intelligence teams conducted forensic inspections of captured U-boats at facilities across Britain and captured European ports. The physical evidence inside the surrendered hulls tells a story of prolonged operational stress that supplements and confirms the documentary and testimonial evidence compiled during the war. Interior surfaces throughout the pressure hulls show heavy diesel residue deposits from incomplete combustion and inadequate ventilation. Extensive corrosion damage affects electrical systems, piping, valves, and structural members. The long-term humidity exposure has degraded insulation, corroded contacts, and weakened materials throughout the boats. British cumulative interrogation files, compiled from hundreds of interviews with U-boat prisoners over the course of the war, consolidate vast quantities of data on training, equipment specifications, operational procedures, and crew experiences. These files become primary source material for post-war analysis and historical research. The detail level is remarkable. Analysts know the capacity of food storage, the duration of battery endurance under various load conditions, the range and speed characteristics, and the specific hardships crews endured. The picture that emerges is comprehensive and damning. The U-boat campaign was conducted beyond sustainable human factors limits from its inception, and the design compromises that enabled offensive capability simultaneously ensured eventual defeat. Post-war submarine medicine literature, published in medical journals and naval technical publications, codifies the confined air hazards documented during the war. Carbon monoxide poisoning from diesel exhaust, nitrogen dioxide damage to respiratory tissues, chlorine gas exposure from battery compartment leaks. These are not merely theoretical risks but documented causes of injury and death aboard submarines of all nations. The medical understanding of hypoxia and hypercapnia advances through wartime experience and research. The neurological and respiratory effects of prolonged exposure to degraded air chemistry become well-established medical facts rather than speculation. The strategic balance sheet of the Atlantic U-boat campaign can be calculated with post-war clarity. Germany constructed and commissioned approximately 784 U-boats of all types during the war. Of these, roughly 690 are lost to enemy action, accidents, or scuttling. Allied losses in the merchant marine are indeed catastrophic: thousands of ships sunk, tens of thousands of sailors killed. Yet these losses are offset by production capacity and escort innovation that the German submarine force cannot match. The cumulative tonnage sunk by U-boats peaks in 1942 and declines thereafter as Allied countermeasures prove increasingly effective. The submarine force cannot solve its fundamental atmosphere problem within the constraints of the Type 7 hull envelope and the industrial capacity available to Germany during wartime. Engineering solutions exist: better ventilation, chemical air scrubbing, improved hull design, enhanced habitability, but implementing them requires resources, time, and production capacity that are consumed by other urgent priorities. The diesel-electric submarine operating concept reached its technological and operational limits during World War II. The next generation of submarines will require fundamentally different propulsion and life support systems to remain viable. The human cost of the U-boat campaign overshadows even the material losses. 28,000 men dead represents not merely a statistic but the destruction of a generation of trained personnel. The institutional knowledge, the operational experience, the technical expertise, all lost. The psychological toll on survivors, though less quantifiable, is equally severe. Men who endured the prolonged stress, witnessed the deaths of comrades, and survived when so many did not carry lasting trauma that affected them for decades. The lessons are clear in retrospect. Offensive capability cannot indefinitely substitute for crew welfare. Design trade-offs that sacrifice habitability eventually impose operational penalties that tactics cannot overcome. Human physiology sets absolute limits that doctrine must respect. The next generation of submarine designers will treat air handling and environmental control as primary weapon systems, essential enabling capabilities rather than secondary comfort considerations. The price of learning these lessons, paid in the North Atlantic between 1939 and 1945, was measured in thousands of lives lost in dark water. The design teams working on next-generation submarine concepts at Portsmouth Naval Shipyard in Britain and Electric Boat Company in Groton, Connecticut study the technical intelligence findings from captured German boats with careful attention. The lessons learned inform every aspect of post-war submarine development. Air handling systems move from secondary to primary importance in design specifications. Crew habitability becomes a recognized operational requirement rather than a luxury. The understanding that human performance under stress depends critically on environmental conditions shapes hull design, machinery selection, and operational doctrine. American naval architects working on the Tang-class submarines incorporate forced ventilation, air conditioning, and enhanced dehumidification as baseline requirements. British designers developing the Porpoise-class apply similar priorities. The Soviet Union, studying captured German boats and interrogating former Kriegsmarine personnel brought to the USSR, reaches comparable conclusions. Every major submarine operating navy emerges from World War II with enhanced appreciation for the human factors that determine operational effectiveness. The technical specifications begin listing crew endurance limits alongside weapons load and speed parameters. Nuclear propulsion, under development in parallel with advanced diesel-electric designs, promises to revolutionize submarine operations by eliminating the need to surface or snorkel for engine combustion air. The United States Navy's nuclear submarine program, led by Admiral Hyman Rickover and supported by industrial partners, focuses on this transformative capability. A nuclear reactor requires no atmospheric oxygen for operation and can generate electrical power continuously for weeks or months without interruption. This enables truly unlimited submerged endurance, constrained only by food supplies and crew tolerance rather than battery capacity or air chemistry. Yet, even nuclear power does not eliminate the need for effective life support systems. The atmosphere inside a sealed hull still requires active management. Carbon dioxide must be removed through chemical absorption or other means. Oxygen must be replenished, either from stored supplies or through generation from seawater electrolysis. Temperature and humidity must be controlled to maintain equipment reliability and crew health. The technical challenges are substantial, but the strategic benefit, unlimited underwater endurance, justifies the investment. The USS Nautilus, commissioned in 1954, demonstrates the feasibility of nuclear submarine operations and validates the design approach. The memory of the U-boat campaign influenced submarine design and operational doctrine for decades. Every navy that operates submarines studies the German experience, extracting lessons about what worked, what failed, and why. The technical reports, interrogation files, and post-war analyses become required reading at naval colleges and submarine schools. The specific details vary by nationality and technological context, but the fundamental conclusion is universal. Submarine effectiveness depends as much on maintaining crew health and performance as on weapon systems and tactical doctrine. The men who served in U-boats, those few who survived, carry their experiences throughout their lives. Post-war memoirs and oral histories record their stories, providing first-hand testimony to the conditions they endured and the psychological toll of submarine service under extreme conditions. These accounts complement the technical documentation and official histories, adding human dimension to the statistical record. The condensation dripping from overhead, the smell of diesel and unwashed bodies, the sound of depth charges exploding in the darkness, the crushing fatigue of weeks at sea. These sensory memories persist long after the physical scars have healed. The British and American public, largely unaware of the specific hardships endured by enemy submarine crews, gradually came to understand through documentaries, books, and films that warfare at sea was brutal regardless of nationality. The heroic narratives and propaganda that characterized wartime reporting give way to more nuanced historical treatments that acknowledge the courage and suffering on all sides. The U-boat men are recognized as professional sailors who served their country in extraordinarily difficult circumstances, even as the cause they served is understood to have been unjust. The physical artifacts that remain tell their own story. Preserved U-boats, displayed at museums in Germany, Britain, and the United States, allow visitors to experience the cramped quarters and oppressive conditions firsthand. Walking through the narrow passageways, seeing the tiny bunks, examining the crude toilet facilities and minimal galley, most visitors emerge with new appreciation for what it meant to live and fight in such an environment. The boats themselves are monuments, not to glory or triumph, but to endurance, sacrifice, and the terrible price of industrial warfare conducted beneath the waves. The Atlantic submarine campaign of World War II occupies a unique place in military history. It represents the culmination of diesel-electric submarine technology and operational doctrine developed over several decades, tested to destruction under wartime conditions, and ultimately found wanting against the combination of Allied countermeasures and the fundamental limitations of human physiology. The campaign succeeded in destroying thousands of merchant ships and killing tens of thousands of Allied sailors, yet failed to achieve its strategic objective of interdicting British supply lines sufficiently to force surrender or negotiate peace. The human dimension of the campaign, the approximately 40,000 German submariners who served, the 28,000 who died, and the survivors who carried physical and psychological scars for the rest of their lives, reminds us that warfare is ultimately about people. Technology, tactics, and strategy matter enormously, but they operate through human agency and are constrained by human limits. The U-boat campaign pushed those limits beyond sustainable thresholds and paid the inevitable price. The lessons learned continue to resonate in modern submarine operations. Contemporary submarine designers understand that crew welfare directly impacts operational effectiveness. Environmental control systems, habitability features, and life support equipment receive priority attention in design specifications. Operational doctrines recognize that pushing crews beyond their physiological and psychological limits produces diminishing returns and risks catastrophic failure at critical moments. The Atlantic of 1939 through 1945 is long silent. The boats lie scattered on the ocean floor, slowly corroding into rust and memory. The men who served in them are nearly all gone now, their stories preserved in archives, memoirs, and oral histories. What remains is the historical record, a detailed, documented account of a campaign that combined technological sophistication with human endurance, strategic ambition with tactical innovation, and ultimately taught lessons that were written in the condensation on steel bulkheads and paid for in lives lost beneath dark water. What is your perspective on this part of history? Share your thoughts in the comments, because every memory and reflection helps keep the past alive.